Hi everyone, this is Mrs. Bustamante. We're still in 8.5 Community Ecology. We just kind of wrapped up talking about Simpson's Diversity Index, and now we're going to start to talk more about how populations or things, community interactions, right? How different organisms within that community interact together. Because communities change over time based on what these interactions are. Right, so to start us off, I want to kind of talk about two things. I want to talk about the difference between habitat and niche, right? So a habitat is just where an organism lives. And a niche is where an organism lives, but it also includes what kind of that organism's role is in the community. We say sometimes it's kind of their job in the community. And what that does is having a specific niche is it sort of allows for something that we're going to learn about in a second called niche partitioning, right? So that ecosystem really gets used kind of to its fullest. And it allows it to be more diverse because specific organisms will kind of find certain areas that they can really specify and be great, if you will. And sometimes you'll hear that's my niche when people are talking about it in their regular lives, right? Just a way of talking about something that they're kind of really good at in a way. So when we're talking about organisms, it's where we really see them interacting with the environment in a very specific way. And this comes about a little bit because of competition, right? There are competition between all organisms in a species and between different species, right? For food, space, mates, all things that help kind of lead to what we see as our realized niche, right? Where an organism actually is going to live. Because two species cannot occupy the same niche at the same time forever, right? They can have some overlap and interaction together, but they cannot be there the whole time, right? It doesn't work out. There will be limited resources. So what we get from that is something called resource partitioning or niche partitioning. Basically, it's like dividing up the area and kind of making the most of it where we find a specific species. Here are warblers, birds, and we'll notice that these birds look kind of mostly the same, but then they look a little bit different. They maybe sometimes have some differences in their beaks or their body types, how they can access typically food, but other things. And we'll see them all in the same pine tree, but live in different areas because that is their niche. That is where they fulfill the role of what they need to do. And this can help reduce competition across areas, right? But really allows for a more diverse community based on these interactions. When we talk about niches, there are kind of two things I like to talk about. There's this idea of the fundamental niche, and this is like where that organism could be found in theory, right? It's the range of conditions under which it can live. And it's typically bigger than what we call our realized niche. These are the conditions where we actually find that organism living, okay? Because when we look at these, I'll try and move this over a little bit, there's like a range that an organism could be at, but then there's kind of like a sweet spot where they really are based on reality or where we see most of them, okay? One example of this is these barnacles, right? Okay, without competition from other barnacle species, right? Barnacle A could be found in all of this area. Notice it's on the land and it's in the water, right? It could be found in both locations. But when there's, say, barnacle B present too, we notice that we don't see barnacle A in the water, right? We see that its realized niche becomes up here kind of on the land because it can survive there, and maybe barnacle B can outcompete it, if you will, for this ocean space. So we have our fundamental and our realized niche. When we talk about competition interactions, they cause change, right? Many different interactions can lead to changes in populations. Those interactions between organisms can be positive, they can be negative, and they can be neutral. So this is where we're going to talk about those interactions as far as mutualism, commensalism, predator-prey, and parasitism. Kind of those relationships you're probably a little bit more familiar with. So what are some positive interactions between species, really, right? Well, the first one, these are called symbiosis, right? Different organisms interacting together is just symbiosis. So when we talk about symbiosis, we can talk about mutualism and commensalism. Mutualism is where both species benefit from their interaction together. And the classic example of this is kind of your clownfish and the anemone. Because the anemone will protect the clownfish, and the clownfish kind of provides some things that the anemone needs too. So both of them benefit from their interactions together. Then we have commensalism. It's where one species benefits, but the other is not harmed. So you'll see +0, right? Here's a whale, right? And there are barnacles on this whale. The barnacles on this whale are kind of like catching a ride to where they need to go or where they might want to propagate, where there's more space perhaps, but the whale isn't really benefited or harmed by these barnacles in any sort of way. Some negative interactions. This is our predator-prey, right? One species uses the other for food source. Here's your hare and your hare and your lynx, right? And the lynx is going to catch the hare to eat it, so the hare doesn't benefit because it dies. And then parasitism. One species benefits and typically the other one is harmed. When you're the parasite onto the host, right, it's not really its intention necessarily to kill it, but sometimes it becomes so weak and broken down that the host, the organism that the parasite is on, will sometimes end up dying. What are some neutral interactions, right? A neutral interaction is where one species really doesn't impact the other one. So when we look at deer and rabbits, here they happen to be on the road trying to cross over, but them living in the same forest really doesn't influence one another or the survival of one another. They're just both kind of there and interact. So sometimes when we look at these, we're going to have to look at models of population relationships. And one of the most common models of population relationships is this predator-prey relationship. And when we look at them, you'll see graphs like this. They typically look kind of cyclical, right? Oftentimes the prey population in size is higher than the predator population, which makes sense, right? When we think back to our trophic levels, the prey population is supporting the predator population. We know about our 10% loss rule. So we know that there's typically not as many organisms as you move up a trophic level, right? But we'll notice both of them are cyclical. And over here is our cyclical hare-lynx relationship as well, where the hare is eaten by the lynx. And what we tend to notice is that the prey population will say peak or have a valley, and the predator population sort of shortly follows that, just a little bit after, right? Because it's dependent on the prey population. It's kind of like reacting to what happens in that predator-prey, that prey population. So we see increases and the predator population occur, and then slightly after the prey population will increase and vice versa. A good relationship to look at. And the last modeling relationship I want to kind of talk about in this video is something called a trophic cascade. And trophic cascade is really the negative effect of the removal or the decrease in a key species in, say, food pyramid, for example, or a trophic level, and how that one decrease can influence everything else, other trophic levels, right? So populations can experience, let's say we have our wolf here, we have some deer, and deer, right, eat plants, okay? So if we remove this wolf, our trophic cascade, it has trickle-down effects, I guess you could say, right? Because there's nothing to eat now, or less things, at least nothing here, right? And to eat these deer, the deer population will go up. The deer population going up is going to cause the trees to get eaten more, or things that the deer eat, right? So we're going to see the population, if you will, of those go down. Whereas here's where it would look like under normal, if you will, conditions. So when we see a key species in a trophic system get extinct or something happen to it, populations can experience exponential growth or exponential death with the removal of that key species. And this can result in interruptions of the flow of energy through an ecosystem and resource availability, right? Because remember, when we're talking about these, they're all interrelated by the energy they give from one to the next. And so those species populations will influence the energy available. I hope this was helpful, and I'll see you again soon.